Our first speaker is joining us over Zoom. Zachary Espinosa from the University of Washington will be talking about DLESyM-Ocean, a deep learning model for upper ocean and sea ice simulation.
Cool. Everyone can hear me? Can I take it away? Yeah, I'm just gonna assume thumbs up. Um, yeah, sweet. Okay, so yeah, I'm sorry everyone I couldn't be there in person. It's really unfortunate. But yeah, thank you guys for attending this talk titled DLESyM-Ocean, a deep learning model for upper ocean and sea ice simulation. This is the last chapter of my thesis. Before I start, I just want to give like a huge thank you and shout out to the DOE CSGF. You know, most of the wonderful experiences that I had during my PhD would not really have been possible at all without the DOE, and all of like the support that this came with this fellowship. And then I also, in particular, this project with all of the HPC, like quite literally, this project would have not gotten done without it. And then I also want to thank the other donors and supporters throughout the rest of my PhD, including like the ARCS, GEM, the University of Washington, GSEE, NSF, and then of course like collaborators at NVIDIA. Okay, let's get started. Okay, so before I actually jump into kind of results and some of the actual work that I did, I just want to bring everyone up to speed on the state of AI weather prediction. Um, and I think this revolution that's kind of happened behind the scenes in just the last couple of years. And so traditionally, like weather prediction occurs in these large numerical weather models that solve sets of differential equations known as the primitive equations, and then physics equations related to chemistry and other radiation schemes and things like that. And they assimilate observations from satellites and from weather balloons and other ground station data. And they step it through this differential solver, and then actually forecast what the global weather will look like tomorrow and the next day, and they kind of roll these out autoregressively. And recently, AI, starting in about 2022 and 2023, AI models finally showed that they were actually able to surpass numerical weather prediction systems in their skill of forecasting global weather. And so how do most of these AI weather prediction systems actually work? They take in an input weather states. You can think of this as like the global temperature and pressure and wind speed fields around the world on a gridded, let's say, quarter degree global grid today. And then you feed that into kind of like these bespoke AI models, and it predicts the states of, temperature, wind, etc. tomorrow. And to be very clear, this is not like, very similar to asking like Gemini or one of these LLMs to forecast it. These are bespoke, specific models that are trained for this task. You can then take that prediction for the next states, you can feed that back into the model, and it'll forecast the state after that. And you can kind of roll this out auto-regressively for arbitrarily long lead times and get a forecast out to, let's say, 15 days or 21 days. And here I'm just showing a figure from what's a model called GraphCast by Remy Lam in 2023. And this was kind of the first model to demonstrate across the board that these AI models could actually do better than our state-of-the-art traditional numerical weather prediction systems. The other thing I also want to mention is that these AI models are not replacing the traditional numerical weather prediction systems, even though they're more skillful. And that's because they directly depend on the weather prediction systems from, National Weather Service and NOAA. And our other Department of Energy agencies. And so big emphasis on that. These AI systems are not replacing them. They kind of are augmenting and enhancing capabilities. And we kind of need continual investment in these traditional numerical weather prediction, including observational frameworks and whatnot. Okay. And so to really highlight the point that these models are now doing better, here I'm showing a common scorecard. On the x-axis is lead time in days. So this is a 1 day, 3 day, 5 day, 10 day, and 15 day forecast. IFS Ensemble is like the state-of-the-art numerical weather prediction system. And then each of these little boxes is the root mean squared error of that forecast at that lead time for this specific variable called like geopotential. You don't have to worry about what this actual variable means. Just know that it's one of the important meteorological variables. Gray is the baseline, so IFS Ensemble. And then blue means that model is actually performing better than the IFS ensemble, and red means that it's performing worse. And each of these other rows is showing a different AI model. And what you can see is actually that like the vast majority of these AI models are outperforming the numerical weather benchmark at pretty much every single lead time. And if you look at other variables, it's true pretty much across the board that these AI models are now surpassing them in skill. But this doesn't go without some limitations of the existing models. So first, oftentimes these AI systems are unstable. So here I'm showing an annual cycle of 500 hectopascal geopotential height for a full year of an autoregressive rollout. And the red means like, deep red essentially means that the model has drifted and blown up. Um, and the challenge here is that because they're autoregressive, there's a little bit of error that accumulates on every step. And that error eventually snowballs and pushes the model out of a realistic climatological state. And this is a challenge because it limits the ability to essentially do subseasonal to seasonal forecasting and thinking about weather kind of on longer timescales. Making these AI systems at the moment kind of inadequate for longer lead time forecasting. Another main limitation, like I just mentioned, is that they're really poor at longer lead time forecasting. So this is a figure where on the y-axis is RPSS. This is just, a measure of skill for weather forecasts. On the x-axis is weeks in lead time. And this is a competition from ECMWF WeatherQuest. So this is like a global competition to see which agency can produce the best subseasonal to seasonal forecasts of weather at 4 to 6 lead times. RPSS 0 means that it's basically a zero value forecast. 1 means that it's a perfect forecast. And our state of the art right now is around 0.05. So we are, pitifully low and barely beating climatology. And I think this is kind of a next axis for us to try and push on in AI weather forecasting. And then the last big limitation of the existing AI systems that are kind of continuing to be developed is that the vast majority of them only simulate the atmosphere. But we know that the Earth system has multiple components. It has an ocean, we have land and soil moisture and vegetation. We have a cryosphere with ice sheets and sea ice. And each of those things are important in their own right, and then also provide predictability to the atmosphere on longer timescales. And so even though we've achieved a lot by only simulating the atmosphere, I think the next generation of models is going to have to push beyond that and forecast or kind of model other components of the Earth system. And here I'm just highlighting some of the most seminal work that's been done, and pretty much all of it has been atmosphere only. So these first two models, GraphCast and GenCast, are by Google DeepMind. But FGN is also from Google DeepMind. AIFS is from the leading European agency. Aurora is from Microsoft. ForecastNet is from NVIDIA. And then this is from a Chinese research agency. Okay, so the guiding kind of question that we had was, given these limitations, can we produce a skillful, stable, probabilistic AI system for simulating the upper ocean and sea ice that we can then couple to some of these autoregressive atmosphere models to give us skill at longer lead times and also to address some of these questions like stability? Um, And so that now I can finally introduce this model that we've called DLESyM-Ocean. DLESyM-Ocean essentially takes in oceanic and sea ice conditions at our current initial condition time. So SSTs, this is like upper ocean temperature, sea ice concentration, sea ice thickness, sea surface height, temperature, and salinity down to about 300 meters depth in the ocean. And then it generates a forecast 4 days into the future. And then we can kind of take that forecast and feed it back into the DLESyM and auto-regressively roll it out to generate forecasts. I won't go too much into the actual details of the model. It operates on what's known as the Heel-Pix grid. This is very common in astrophysics. It's like an equal area isolatitude grid and has some really nice properties for modeling like Earth system and geospatial data. And then DLESyM under the hood is a UNet using like these specialized convolutions that operate on the Heel-Pix mesh that we kind of optimized with a team of engineers at NVIDIA. Yeah, I'm happy to answer any questions kind of detailing the architecture of this. And then the other detail here is that this is a probabilistic model, not a deterministic model. I'll talk more about that in the next slide, but what that means is that we're actually injecting a little bit of noise or stochasticity into the model each time, so that for a single set of initial conditions, we produce a large ensemble of potential outcomes of forecasts. Yeah, okay. So like I mentioned, so there's kind of two paradigms for models. There's deterministic, which take one set of initial conditions and produce one forecast. And those models are typically trained on what's known as RMSE, which I'm sure many of you are familiar with. But one of the big limitations of RMSE is that it causes severe blurring because the optimal solution to RMSE is conditional expectation function. And this kind of fails to capture the range of possibilities of a real forecast. And so recent models have kind of moved to being more probabilistic. There's many different ways to actually train probabilistic models. Some people use diffusion and generative approaches. Others have kind of converged towards this thing called CRPS, or continuous ranked probability score. This is essentially taking one set of initial conditions and actually generating an ensemble, let's say of 50 different forecasts. Um, One of the big limitations of CRPS, though, is that it's calculated pointwise on marginal distributions instead of joints. And as a result, it is very prone to having spatial artifacts. Like in this panel here, I'm showing it's banding, which is physically unrealistic. So both of these have their downsides. One results in smoothing, and you can kind of see that in some of these spatial gradients here. And the other one is prone um, to spatial artifacts. And so one of the novelties of our approach is we introduced this new thing called a patch energy score, which essentially, I won't go through the details of this, but it essentially is a multivariate generalization of CRPS, which is performed on joint distributions rather than on marginals. And so we get that probabilistic benefit while also preserving spatial coherence. Happy to talk about this in more detail if anyone has questions. Okay, I'm running short on time, so I'm just gonna dive into actually a couple of the results. The first is that we show that DLESyM-Ocean is actually really quite skillful at long lead times. So on this x-axis, I'm showing number of days. On the y-axis, I'm showing RMSE for upper ocean surface temperatures and then for sea ice concentration. These two gray dotted lines are climatology and square root two climatology. So you can kind of think of these as like baselines, like statistical baselines for performance. This black line is a persistence forecast. So you can also think of this as like a baseline forecast. So we need to beat all of these for it to be actually useful. The solid gray line is the ensemble mean RMSE for a 50-member ensemble. And you can see like we're definitely, crushing both of our baselines. The RMSE, this is the RMSE of an ensemble member, the dotted line, and then the dashed is the spread. And when the spread and the ensemble spread and the ensemble RMSE are roughly overlapping, that gives you a spread skill of 1. That essentially means that your model is well calibrated and generates a realistic, distribution of potential outcomes given some uncertainty within your initial conditions. And so this panel is actually just highlighting that. So here, instead of taking global averages, like I've done in this and just showing it as a function of lead time, I take a single time slice at 80 days and show the spatial map of RMSE for the ensemble mean and then spread. And you can see that they have really, a very strong pattern correlation or agreement between the two, such that regions with a lot of error meaning that they're less predictable. They're driven by a kind of eddy kinetic energy, also tend to have the most spread. And when you take the ratio of these two plots, what we want to see is exactly 1. And that is indeed, we see pretty much everywhere the model is fairly well calibrated, close to 1 spread skill. So these early results suggest that DLESyM-Ocean could be useful for subseasonal to seasonal forecasting if coupled with an autoregressive atmospheric model. Yeah. And then just a couple other key results is that DLESyM-Ocean is stable for very long rollouts. So here I'm showing global mean temperature between our observations in black and DLESyM-Ocean, and then different climatology maps of SSTs and sea ice, and DLESyM-Ocean shows very little drift even for very long lead times. Sea ice is a very similar story. For the patterns of sea ice concentration, sea ice thickness, DLESyM tends to perform very well relative to ERA 5 or observations. even for long lead times. We can look at a couple different case studies. So this is like a marine heat wave that occurred in the Pacific Northwest off the coast of California and Washington. And you can see that we were able to produce SST anomalies consistent with observations in black really quite well, where each dotted line here is a different ensemble member, and then different realistic patterns of SST anomalies. And then I'm going to skip this for the sake of time and kind of just go straight into the conclusions, which are DLESyM-Ocean was trained on a patch energy score, which is a novel contribution. It seems to be relatively well calibrated and skillful for several months. It's stable for out to 5-year simulations. And then we tested it on a variety of case studies, including looking at Antarctic sea ice and and the blob and so on. So I'm happy to take any questions. So sorry I had to kind of rush through the last part of that, but yeah, thank you.